Hello, today we are going to make decisions from our sampling distributions data, and we're going to do this with 95% confidence. And if you think about that 95%, that's really, really important because that's the number that we use when we talk about the 60, 95, 99, 7 rule. So we know that that's 2 standard deviations from the mean, and 95%, if I got a 95% on a test, I'd be pretty happy because, that's a pretty strong A, we'll say, where we're very confident of something occurring. We can't ever be 100% confident. If you think about how many texts did you send yesterday, that number is going to vary quite a bit, and we can never really be 100% confident because of natural sampling variability. So if we look at rolling one die, for example, this would be the distribution on the left, where basically we would expect a 1, 2, 3, 4, 5, and 6 to occur with the same probability. Now, they're never going to be perfectly flat across. They're going to be maybe vary slightly from that. So you might see one be a little bit higher, maybe one be a little bit lower, maybe, here, maybe this guy go up a little bit, and so on. So if we're rolling a die, let's say 60 times, and I got 12 twos, that really wouldn't surprise us that much because we would expect to see 10. We would expect 1/6 of them. Let's say, on the other hand, I got 2 twos. This would really wow us because we would expect there to be 10. So this 2 is very, very unlikely to occur. So we're going to see what's the probability that that number occurred for it to have happened by chance. And we want to say that 95% confidence is the number that we're going for. So that's what we're looking at today. So if you go ahead and you look at the notes, today we're going to be making conclusions based off of our z-scores. And this is really the introduction to a foundational in inferential statistics, where we're looking at inferential statistics. So this is the z-score we've been looking at when we're looking at our mean of a whole bunch of different samples. So x bar is the mean of our sample, mu is the mean of our population, sigma is our standard deviation population, and n is our sample size. So if we are making decisions, anything outside of 2 standard deviations means it is statistically significant because it could not have happened by chance. So we're saying that 5% that is so unlikely because 95% in the middle and then 5% on the outside, where this is so unlikely that we don't believe it happened by chance. So here's how a problem like this looks. The Doritos company claims a small bag of chips should contain 12 chips with a standard deviation of 11.4. So we're claiming it's going to have 12 chips. That's what the real average is, and the standard deviation of 1.4. From a sample of 12 bags, so we're looking at 12 bags, that mean was only 11.2. So remember that x bar is our sample mean. We want to know, are they ripping us off? We're expecting 12 ounces, but we're really only getting just over 11 out of 12 bags. How unlikely is that to have occurred? So if we look at the z-score, that's going to be x bar minus mu over sigma over root n. After we plug this into our calculator, we get negative 1.98. So in this case, we are not quite 2 standard deviations away. So we look at that normal curve, we're expecting to be at 12, and we're over here at 11.2. This is not quite 2 standard deviations away. It's just 1.98 standard deviations away. So this is just on the threshold of not making it to 2 standard deviations. So we can't say that we are believing that it's statistically significant because we have to have a cutoff of that 2 standard deviation. So in conclusion, we do not have enough information to believe that Doritos is underfilling their bags. So we do not have enough information to believe Doritos is underfilling their bags. And this is because Z is greater than -2. All right, so same thing in the next one. We're going to go through, find the z-score, and see if we make it to a statistically significant value meaning our z-score is further than 2 standard deviations from the mean. So this one is, Jimmy John says they're so fast, so free because they claim to have your food delivered in 10 minutes with a standard deviation of 1. So the claim is what we believe to be true, which is our true mean, and the standard deviation is 1. However, from 8 orders, the mean delivery time was 12.2 minutes. Oh no. So is this statistically significant where 12.2 is so far from 10, we can't suggest, or we can't think that 10 minutes is the true delivery time. So we take x bar minus mu over sigma over root n, plug that into your calculator, and we get 6.22. Wow. Right? This is way more than 2 standard mean. So at 10 minutes, when we're way out here at 12.2 minutes for an average of 8 orders, this z-score is bigger than 6.22. So that means that that's very, very unlikely to occur. So think about that 3 standard deviation cutoff of 99.7% of your data. This is even further than that. So we're so far above the mean that we believe that this is statistically significant. So in this one, so in conclusion, we believe that Jimmy John's is inaccurate in their 10-minute claim, and the delivery time is truly greater. So in conclusion, you will be looking at a mean and a standard deviation. You will take your sample mean x bar with a certain sample size of n and look at that z-score. If that z-score is so far from the mean, and we call so far anything past 2 standard deviations or negative 2 standard deviations from the mean, we think that the true mean is no longer true. So I know that sounds like a lot of words, but we do, for example, in Jimmy John's, they claim 10 minutes. It is no longer 10 minutes. We think that that is an inaccurate claim. And as I said, this is the foundation of inferential statistics. So look for z-scores further than 2, and that suggests that the claims of the true mean are inaccurate and that we have a statistically significant value. If that z-score is further than 2 standard deviations away, we have a statistically significant